we begin our studies with Twin Delayed Deep Deterministic Policy Gradient, aka Td3 algorithm. So Td3 has 6 neural network. One is the main actor network and the other is target actor network. The main actor network is responsible for taking an action. So the action is equivalent to a policy pi parameterized with alpha, and which is a function of this action that was taken in this specific state. And the policy aims to maximize a K value. So the K1 and the K2, which correspond to this main critic 1 and then the main critic 2. In the main critic network, these two network aims to minimize the inherent overestimation vulnerability in K-learning algorithm. So this is to achieve to minimize the overestimation or to eliminate the overestimation. So MC1 tries to minimize this Q value when it is doing the training. The main critic 1 has a corresponding target critic network, and then the main critic 2 also has a corresponding target critic network. So that a loss is computed in between them. Now, how is the K1 achieved? Now, K1 theta is achieved as this. Now, because we have a Q1 here and Q2 here, we write it in the compact form as Qn, and the n is equivalent to 1 and 2 in this action and then state. And because we have theta here and theta here, we write theta exponent n, and then we bring 1 here in a more compact form. So this Q value is achieved as this. The Q value for the main critic network is achieved as this. So this is a learning rate, and this is the expectation, and we open a bracket, then the initial reward plus a discounted reward. This is gamma, and this is this whole expression here is the target Q value. Target Q value. Remember, the target Q value is a stable Q value. So this is a predicted Q value, and then the predicted Q value aims to achieve this target Q value. So this whole expression is denoted as this. Now there is a Q prime, and this is L equals 1 and 2. So here we have Q1 and Q2. So we don't want to write 1 and 2. So we denote it with L, and we bring 1 and 2 here. Remember that when L equivalent to 1, it means we are talking about this expression, and when L is equivalent to 2, it means we are talking about this expression. So now that we know the target and then the predicted, it means we can compute the loss. So the loss for this gradient is the loss, which is a function of the theta, is equivalent to this. This is the expectation, and this is the whole predicted. In the reinforcement learning, the loss is computed as the predicted minus the target. Then we square it. So this is the TD error. So this is a temporal difference error, because this is a predicted and there's the target. So this is the TD error. So how do we achieve the next weight for this network to perform training? We achieve it through stochastic gradient descent. So we take a gradient of this loss value with respect to theta. So this whole expression. So we took the loss. We differentiate this expression with respect to the theta, which is equivalent to. We also do the same thing for this whole term, and then there's an expectation, and the dot here is for the whole of this term. The whole, we don't want to write it again, so the whole of this term. Then after achieving so after getting that weight, we update it. So this is update. So triangle up is the update, and then the theta n equal theta exponent n equals 1 and 2. I've explained that one already. which is equivalent to the old theta. So remember, this term is different from this. This is the old theta minus a learning rate dot the derivative of the loss function. That's the derivative. This we bring the whole of this expression here. So this is the whole as this is the same as this. Then let's go to equation 5. So in equation 5, we can now update the target critic weight. So this is the main critic weight, and the target critic weight is equivalent to this. So you see this expression from here to here is the same as this one. So we copy this one. So that we copy it, and then we multiply it with a tau. So the tau is the smallest time interval at which this whole weight is copied, plus 1 minus tau multiplied by the initial weight of the target critic network. So that is the training that the critic network goes to. Then the loss can now be computed for the main actor network as the argument. So after this loss has been computed, or after this Q value has been computed, the one with the minimized Q value is now used to compute the policy gradient. Notice that this and this are there to achieve a minimized Q value to prevent overestimation. So the loss is now computed at argument. So any of the Q values that has the minimized Q value is used to compute the loss. So we have Q1 and Q2, and then you have the policy that the actor took. So this is the objective function that the main actor has. Then we can now compute the new weight of the main actor as the derivative of this whole expression. So the derivative of this whole expression with respect to alpha. So this is the derivative of this whole expression with respect to alpha. Then after, we can then update it. So the triangle up means we want to update the new weight that we got. So the new weight is equivalent to the old weight minus the learning rate of the derivative of the loss function, which is equation 8. Then having found that, we can now update the target actor network. So this alpha prime is the target network, which is equivalent to the tau minus this whole expression here, which is this, plus 1 minus tau, and then the alpha prime. The alpha prime is the old weight for the target main critic network. Thank you very much.